Today we're going to look at how to use logarithms and logarithmic models to express data so that it is easier to determine what's going on and how to find the relationship between two specific values. Sometimes we have data where both x and y are changing rapidly as we move left or right. These data tend to be skewed. They tend to have a shape that's stretched out at one end or squeezed down at one end. And these are examples where we're looking at the actual average distance from the sun measured in astronomical units. One astronomical unit is the average distance from the sun to the Earth. And we're looking at the period of orbit in Earth years. So if we're looking at this, we're going to try and use logarithmic transformations to see how those log transformations can affect our plots. So what I'm going to start with here is I'm going to go ahead and enter all of these data into my graphing calculator using my stat button. So I'm going to start by pressing stat. We want to choose edit by pressing enter. And I'm going to enter all of my A values into L1. I'm going to enter all of my T values into L2. Now into L2, I'm going to go ahead and enter all of my T values. I want to make sure everything lines up horizontally. Once I've got these data, I'm going to go ahead and I'm going to create a scatter plot with them. So in order to do that, what I want to do is I'm going to go ahead and enter into my calculator by pressing second, y equals. I'm going to turn on that first stat plot. I want to make sure that the x list is L1, my y list is L2. And I'm going to set my window. The smallest a value, or x value, is going to be 0.3870, and the largest is 20. So we can set this up so we go from -5 to 20. Our y min and y max, our smallest y value is 0.241. Our largest is 84. So what I'm going to do is I'm going to set up my y min at -10 and my y max at 100. That way I can fit everything in and I'm not squeezing anything. So when we look at these, it's really, really hard to tell what shape they have. They kind of look like they're curving up as we go from left to right, like they're getting steeper. But it's really hard to tell because they're so far apart from each other, so we can't really compare them. So what we're looking at here next is to kind of change these data around. I want to change it up so that I can kind of tell a little bit better how things relate to each other. So I hit this. It looks kind of curvy, but I can't really tell. It looks like it's getting steeper, but it's really close. So what we're going to do is we're going to go through and we're going to use logs to rewrite all of our numbers. So instead of having 0.387, I'm going to have ln of 0.3870. We can have our calculator do that by using what we call list operations. We're going to go back to stat and edit. Now I'm going to scroll over to L3 and I want to scroll up to where I highlight the letter L, or the name of the list, L3. What I'm going to do with that now is I'm going to take all of my numbers from L1, and I'm going to take the ln of them. So I'm going to press ln of L1. This is just like an Excel sheet, and it's going to go ahead and autofill all those numbers in for me. I'm going to do the same thing with L4, taking the ln of L2. So we get all of these numbers here, and when we readjust it and we create a scatter plot of these data, that looks really, really linear. So what I want to do is find the linear equation that goes with that. So these data look linear. So I'm going to use linreg. So I press stat, over to calc, and I'm going to choose number 4, linreg. My x list isn't going to be L1, it's going to be L3. And my y list is going to be L4. And I scroll down to calculate, and it gives me this equation, 1.49947 times 6.95197 times 10 to the negative 4th. So what that's going to end up giving me is something that looks like this. Now, if y equals 1.4994x plus 0.0006, that's essentially going to boil down to y equals 1.5x. It's close. We're approximating a little bit, so we have to round a little bit extra. Now, if we have that y equals 1.5x, remember that y equals ln of t and x equals ln of a. So that means that I have ln of t equals 1.5 times ln of a. And with that, because I have that ln of t and I have that ln of a, I need to get rid of, I'm going to try and get rid of those ln's if I can. I'm going to start by dividing. So I'm going to divide away my ln a. So with this, those ln a's cancel out, and I'm going to be left with ln of t over ln of a equals 3/2. And we know that with that, we can kind of combine those two things using a change of base. Because this right here is a change of base formula. It's just backwards. Instead of going from one base to ln, we're going from ln to a different base. So that means that I'm going to have log base a of t equals 3/2. And in order to get that by itself, I'm going to go ahead and put everything to the, I'm going to do what we call exponentiate. I'm going to say a to this power equals a to that power. These a's cancel out, and I'm left with t equals a to the 3/2. And I promise this is you're going to see where we're going on this. In order to get rid of that 2, I'm going to go ahead and square both sides. And I'm going to get that I could rewrite this whole equation now as t squared equals a cubed. That's going to be super important because Kepler was a really, really big fan of planets. He came up with some major ideas about how planets move. So one of the most consequential things that Kepler came up with is Kepler's third law of planetary motion. And Kepler's third law of planetary motion talks about how the orbits of a planet relate to their distance from the sun. So in this case, what we're going to be looking at is, after he tried a bunch of different things, he found that the square of the periodic times are to each other as the cubes of the mean distances, which is just a really, really, really fancy way of saying the square of the times. So the square of t is 2. When they say is 2, they mean equals the cubes of the mean distances. Where mean means average, so this is the average distances, and that's the equation we got. So even though we couldn't see that type of relationship, because that's not a normal type of relationship, that would be like a weird, funky power regression line. We couldn't see that, but we used ln to kind of solve for it, and it was hidden inside what we already had. So when we're talking about logs, they are really, really useful in helping us to rewrite, reformulate, and in this case, do what we call normalizing. We're taking a skewed set of data and we're making a more normal distribution out of these data.